Okay, welcome back, everyone. Just before we get started with our talk, we've got a couple of messages from our very generous sponsors. We have, firstly, we have Andy from NVIDIA, who's coming up who's involved in the Python CUDA work that's going on. So this is Andy.
Thanks, Simon. Thank you, everybody, for being here. We are super excited to have an AI track here at PyCon and be able to support and help everyone learn how to use this amazing technology that's becoming better every day. We do invite you to come check out some of the Sparks Spark DGX Sparks we have at the Anaconda booth for this afternoon. And we have some local inference models and things you can play with and so forth. And we're also going through the announce of CUDA Python 1.0. And after the session today, we'll have NVIDIA's open space over in 203. So if you want to continue talking about AI in an open forum, we'll have a lot of our NVIDIA staff there. Thank you very much.
And here's Ted and Fabio from Anaconda.
Hi, everyone. I'm Fabio.
I'm Ted.
And we work for Anaconda. Probably you've heard the name, the Python, secure Python packages company. We probably heard about Conda, about packages. And Anaconda does a lot of things. One of them is really contributing and believing in AI. In open source, but also in AI. And that's been the core of the company since we were founded in 2012. And the same way we contributed to a lot of the open source ecosystem, especially data science, enabling developers to do their jobs. We are committed to the AI mission as well, bringing tools to help with that and make AI secure. Yeah.
Well, it's really an honor to sponsor this track. I know it's a very interesting time. AI is changing many things in our daily work. And one of the things we're trying to do is to figure out how to make that output of exceptional quality. And it's an interesting journey, and I really appreciate everybody attending PyCon and joining us on this journey. Yeah. Thank you.
And last 2 seconds, I would just invite you all to find us out at the booth. We have a bunch of new products around AI, Agent Studio and Anaconda Desktop that you can try out and check out. Also invite you to a talk after this one, where we're going to be showing some of that as well and talking about agents. Thank you so much. Enjoy your conference. Thanks.
Okay, and please welcome Aayush Kumar.
Hello, good afternoon, Python community, everyone, and I hope everyone has had their lunch and they don't fall asleep during the talk. I'll try to keep it as interesting as possible. So today I'm going to talk about running large language models on laptop, practical quantization techniques in Python. So who am I? I'm Aayush Kumar, JVS. I'm an AI researcher, I'm a Python engineer and problem solver. And I'm here at PyCon US to present my research and practical techniques for running LLMs on laptops in Python. So most of the work that I'm going to be present today was part of my master's thesis that was published in 2024. And later on, I kind of started working on whatever is possible. So quantization is a process where we are running or compressing of weights, model weights, and activation so as to perform and save on memory footprint. So the impact right now is enabling powerful large language models, which are very huge in size. The latest version of Llama 4 was around 70 billion parameters, and Llama 2 that released in 2023 was around it released in 3 stages, 1, 2, and 3. So they were of 70, 140, and 180 billion parameters, and they were huge to run on. They were really huge to run on laptops, and we would rather require NVIDIA A100 to run those rather than doing simply on our laptops or computers. So people like Tim Dittmers and other AI researchers came together and they came to find a new solution called as QLoRA, which is using quantization as a technique to reduce the lower rank adaptations. And QLoRA and other techniques have been become very famous so as to run LLMs on your laptops. And this is like a very good way to say that LLMs, which can be used for different cases, can be run like this. This is just like how the quantization works right now. And then there will be a range that will be selected during the quantization. And there are two types of quantization that works that are asymmetric and symmetric. And what does k-bit quantization means? So the k-bit quantization is like k-bit is the clustering algorithm like principal component analysis and other. So the k in k-bit is k-mean clustering. So it is where we try to see like faster inference for computation and then memory efficient, hardware compatibility, grouped interpretation and stuff like that. So the key innovation that comes from this motivation was Llama CPP uses k-mean clustering for 4-bit quantization, which groups smaller weights together, preserves the relationship between weights, and minimizes the quantization error in critical mode components. So that's k-mean optimized. Though there are several flavors of k-mean quantization, and this is how the k-quants in quantization work. The S is for compressing everything essential, and then M is for like compressing only the unimportant layers of the weights, and then LX, L and XL is to compress only the least important layers. So right now you can see that if we use quantization, the first image shows that this is the bits and floats 16 quantization, and the image quality is a little bit good. And then later on it is reduced by half to 8-bit quantization. The image has blurred. And then later on when it is reduced to 2-bit quantization, we have like pathetic quality. So that is a trade-off of this talk, that what is the perfect k-quant to choose so as to you do not lose accuracy and you maintain your balance as well. So at least we have seen that 18 labs have released their own equivalents of GPT-4, be it Google, OpenAI, NVIDIA, Meta, Amazon, Anthropic, Mistral, and others. So since every company is releasing their own LLM, open source developers online are releasing a quantized version of that too. So that's the fun part. And being able to use the, like the miniature version of these large LLMs is where the talk is going to be pivotal today, because we are able to use all these LLMs together on our laptops for a pretty miniature version. So GGUF is Georgi Geronova Unified Format. So he was the guy who converted Llama CPP to easily interpretable running formats on our today's LLMs. So what most LLMs you see on quantized LLMs that you see on Hugging Face or other repositories is mostly a GGML or GGUF quantized version. So this is how the GGUF model is working with the general architecture for Llama version 2. And this is how the version takes the rest of the file, and then first 4 bits for GGUF number, and then tensor computation. And then this is how the GGUF architecture looks like. And Bits and Bytes is another famous library which is similar to what GGUF, GGML do. But the only thing is that it kind of uses 8-bit blockwise quantizations to do the same. And LLM int 8 is also coming under Bits and Bytes. So Bits and Bytes is a very famous library for using quantized LLMs. And it's as easy as using pip install BNB, import BNB. So later on, what we'll be seeing today is that how these libraries are being used by people to develop k-bit quantization. So the most popular versions of these quantized models are provided by Unsloth and then by Tim Jobbins, who is like the provider of various GGUF, GGML models, and Bartowski, if that's what I'm pronouncing right, Bartowski. These researchers have published several LLMs quantized version online on Hugging Face, LM Studio, and other resources for free. And everyone can access it to make their own use cases and stuff like that. So the main essence of this is that they do it because they might have fun. That's another thing. But the only reason is like they are being available to everyone right now, and most of it is open source. So right now we can use these LLMs on Olalama and other platforms as well. So like this is Quen, which is I think by Alibaba. And this is like one of the most famous models right now. And this is like their 3.6 billion parameters model, which is quantized down to, 31 GB and stuff like that. So everyone can use it for their task. So what over here, the key quantization terms that we need to check is like Unsloth dynamic, which is UD over here. And the IQ is importance quantization awareness. So what amount of quantization will be put in these LLMs so as to get a refined result is what we are going to see about. And so as you know that we have seen reduced bits of these quantization, there's something exists called as 1-bit quantization too, which is not similar to what the 1-bit model or the bitnet models are. The only reason for these models to be compressed to 1 bit is so as to represent that this is also possible. But the trade-off that is being demonstrated over here right now is that even though we have 1-bit model, we miss out on the accuracy or like the expected results. And they lead into an error called as perplexed. So perplexity is basically the confusion meter for a model that is being perplexed. So it measures confidence, but not accuracy. And that is what is being shown over here, that low perplexity leads to a very small amount of error, and high perplexity gives absolutely bad results. So how to choose the right quant for your use case? So the first rule of thumb, as you might have understood till now, that the larger the model is, the better. Higher quantization rates give higher accuracy. This is highly model dependent and use case dependent too. If your accuracy is of at most important, then you may need a higher quant itself. So over here, what is being demonstrated is that your GPU memory, suppose 12 GB, has model weights, and then your context, and then system overhead. What is really more important than your model weights is your context. That what are we going to use this for, and how much are this context length going to be used for? This is where latest research like TurboQuant and others come in. And this is where how it's being represented. So the reality of running models is that more than model weights, what is important is your context. So is your context still related to the reality of the model and how big it is? So that's why where we try to check the context length of the corpus, and we try to understand that if the model is being quantized efficiently or not for the use case. So how to pick the right quant and the context size? So assuming you have a 12 GB of VRAM and 8 billion parameter model, so the parameter is in billions, and that's multiplied with bits per weight over 8. And that's how we try to measure, like for an 8-bit quantization, we check out 8 cross 8 over 4, and then 8 cross 4 over 8, and then 8 cross 2 over 8. So the less the VRAM for the model, the lesser the intelligent the model is. And later on, this is what the context window is about. This defines us like the KV cache memory, which is being used for quantized. It's 2 cross the layers and into head, and cross head dimension, and then cross context length over 10 power 9. So suppose we use the Qwen 3.5 latest 27 billion parameter model with a full context length of 258 tokens, 256,000 tokens, then we will try to have a space needed of 34.3 GB. And then if we have a full context length of 8,000, then we would require somewhere around 1 GB of space to run the Qwen 3.5 quantized version of the model. So I'll not try to go very deep into the math, but this is just like showing how it's figuring out the head length of the dimension and the architecture, the number of hidden layers and stuff like that, and multiplying and then trying to get it to 1 GB. So all these details on the right-hand side can be found on Hugging Face and similar repositories in the config file. So it's very easy to calculate the necessary amount of model context you want to run on your GB or on your laptop. So where can I find these LLMs right now? So most of the LLMs over here are being deployed on different apps like Llama CPP, LM Studio, Jan, Backyard AI, Rescue Chat, Sanctum, Local AI, VLLM, Node Llama CPP, and Ollama. And I'm sure most of you might have used it too. So the websites for GGML and GGUF are over here with the documentation of how everything is being quantized and how everything is taking the context length and calculating the KV cache memory. So it's very easy to run these on your laptops. I have did it myself, and I'll be showing what I used these for the use case and how it was successful for me, and I'll just demonstrate it later in the talk. So yeah, over here, I kind of use the quantized LLM for my thesis work. This is my thesis where I was using different quantization techniques like QLoRA and parameter efficient fine-tuning, GGUF, GGML, and then this was published with UMBC. Over here, I tried to discuss that how I'm using different corpuses of mental health scenarios and different mental health text data set, and trying to use or almost around like 15 to 20 miniaturized quantized LLMs. And then I was trying to see what is the accuracy trade-off, context length, and memory footprint for every LLM. And that is what it was about. And then, yeah. So, thank you. Any questions?
Hi. You were talking a lot about the memory usage of these quantized models. How does quantization affect energy consumption? For example, if a company wanted to host a server-based one locally, but couldn't manage or didn't want to have to limit individual developers to have a certain number of credits, could a quantized model allow them to have essentially unlimited credits at a much more efficient energy usage?
Yes, I think what my talk was answering is that since quantized versions don't require much space, and if a developer has unlimited credit usage, I think he or she can use it for their use case, and it'll allow a lot of different models to fit in if they use the credits intelligently. Like they can use sequential training methods, and then they can use different quantization techniques. Like there is GPTQ, and then there is AWQ, which is like quantization aware training. And then I think what essentially I want to answer is that if you change the methods, techniques, it'll be able to save more credits too.
Particular approach that's always better, or if I have a data set, should I quantize the model with one technique and then compute perplexity or something and then do it with another technique? Like how do you figure out which is best?
Sorry, sir, I didn't get your question.
If there's multiple techniques, is there one that's always best, or do you try different techniques on a sample data set to figure out which quantization technique you should use?
Well, if you honestly ask my opinion, I feel that quantization-aware training is better than the rest, because the weights are quantized when you're training the model itself, and then going ahead, you don't need to shrink it more. So I feel that is the better version. And like even if you try to quantize, just try to quantize it for a higher K value, because the more less you quantize, you might lose on accuracy and the models will get perplexed. So if you need to save it from being perplexed, you might rather stop it at 2-bit quantization than to stretching it to 1 bit.
So if I hear you correctly, you're saying you pick a quantization technique and then you do training with that quantization technique.
Yeah, that's a quantization-aware training, AWQ. And then there's rest also like GPTQ and K-bit quantization and stuff like that. But and then there's QLoRA, bits and bytes, GGUF, GGML. But the more famous ones that's being used by everyone at Hugging Face and all the developer community is like GGUF and GGML. Since like couple of years, they tried. They took the Llama CPP's entire corpus of models and they converted it to GGUF. So everyone is being able to use it right now. And I think you can also take a version of this and try to quantize it and be able to run on your system. So what I'm essentially trying to say is that the GGUF, GGML models, which were made by Georgy Jernov, is very easy to use and widely available. So since these are very much in resources, any person could, pick and play with them and then use it for their own use case. And suppose I'm like a researcher, so I would take a new model for a new corpus of data set and try to make research with it and try to publish it so that I can present it at new venues and stuff like that. So it's really depending on use case to use case. But what I essentially am trying to answer is that it's widely available right now for several quantization, like there's post-aware quantization training, there's quantization-aware training, and there's QLoRA, which became very famous by Tim Dittmers in 2023. So he was just trying to say that, there's no need for developers to be behind the screen, like a CUDA developer behind the screen and running this large models on their laptops. But it's not like that anymore. So since these have become very high in resources, people in high school also can take and they can use it for their own use cases and they can play with it. So that's what I'm trying to say.
Hi, Aayush. Thank you for the talk. So if I understand your research project, what you are trying to do is you are trying to quantize by stripping away unnecessary layers, unnecessary nodes to get down to the bare bones of what exactly it is, that would give you functional use out of these models. I'm curious, was there a sweet spot of quantization for your use case that you found that was giving you a good balance of performance with also the model not being perplexed and just giving you back random gibberish?
Yes, that's a very good question. I feel my sweet spot for the training was 8-bit quantization using LLM Int 8. And primarily this is because the 32-bit floating BF float 16, BF 32 didn't quantize as much. And the ones which I quantized more were like 4 and 2-bit, which were more more near to the being perplexed. So since my boss asked me to like make the quantized versions of different, he wanted me to run these on mental health corpus. So he wanted me to like make different LLMs on mental health. And that's what I did. I ran it on separate mental health tasks like SG, Reddit, and then Twitter mental health, stuff like that. So I didn't really focus more on the task, but I focused on which model to be selected. So I observed that when Llama 2 and Llama 3 were running on 8-bit, they saved more on memory too, but at the same time they gave a much higher accuracy. So at any time of the day, you would rather want to run a Llama original base model on your laptop than running a separate quantized version of it. But the only advantage of running a quantized version of it is that you would not black out your computer. And that is most essential part of the talk, and that is why it's easier to run the quantized version of these models. And since 2023, after QLoRA was released by Tim Dittmers from University of Washington, the community has shifted to this, and a lot of developers, I told you, right, Bartowski, Tim Hobbins, and then Unsloth have released different quantized versions of these models, with the 1-bit model being produced too. So it's easier, it's very resource friendly, and so the 8-bit quantization was my sweet spot, to answer your question.
One follow-up, were there certain models that responded more positively to quantization versus others that did not perform as well?
Yeah, so the Gamma and Quen models for other versions, like we did even run Mistral and Grok. So the Gamma and Quen versions were not being really producing much good results when compared to Llama and other famous models. So like Alpaca, Vicuna, and stuff like that. So the only thing is that even though we observed failure from these, we had positive results from others, and we kind of like even did sequential training. So we kind of commented 4 to 5 batches of LLMs, and then like I ran Llama 1, 2, 3 together, and then we used Phi, Mixtral, and Quen in the second training batch, and I just worked with the parameters like that, so as to see how results were affecting the memory footprint and the accuracy. And it was fun for me, absolutely, because it was very resource friendly, as the community has become so stronger right now with a lot of stuff that is being produced online regularly. So if you are observing failures, that's a good thing, because you can check out from that and use different models, and you can see that why this is not working better and why this is like a better one. And that can be a niche area of research too one day. So thank you. Thank you, sir.
Thank you very much.